What we just established is the upper bound for theta of x. Now to prove the other inequality, namely, psi of x is bigger than some constant multiple of x, we need the following fact on the prime factorization of factorials. Which is the decomposition of n factorial into the product of powers of primes, where each exponent j of n, p is equal to the summation of the floor of n divided by p to the m, and perhaps a more common notation is nu sub p of n factorial. In number theory, this notation means the p-adic valuation or p-adic order of n factorial. Theorem 416 is often referred to as the so-called Legendre formula. And to help the audience understand this theorem, let me give you the following example. For n equals to 6, let's look at the factorization of 6 factorial. 6 factorial is equal to 720, and its prime factorization is equal to 2 to the 4th times 3 squared times 5. And the exponents j of 6, 2, which is also nu sub 2 of 6 factorial, is equal to 4. And this 4 can also be computed through Legendre's formula by summing up the floor of n divided by powers of p. So in this case, 4 is equal to the summation from I equal to 1 to infinity of 6 divided by 2 to the I. And there are only two non-zero terms in this sum, which is 6 divided by 2 plus 6 divided by 4. And this is 3 plus 1, which is indeed equal to 4. And similarly, j of 6, 3, which is nu sub 3 of 6 factorial, here it is equal to 2. And there's only one summand, which is 6 divided by 3, which is 2. And similarly, you can compute j of 6, 5. This is 1. Now, how do we prove Legendre's formula? To prove this, we'll count the exponent to the prime p in the factorization smartly. First, let me show you the Wikipedia's proof. Wikipedia says the following. Since n factorial is the product of the integers 1 through n, we obtain at least one factor of p in n factorial for each multiple of p in the set 1, 2, all the way to n, of which there are the floor of n divided p many. And now, each multiple of p squared, now we are looking at p squared, contributes an additional factor of p. And each multiple of p cubed contributes yet another factor of p, etc. And if we add up the number of these factors, we'll get this infinite sum for nu sub p of n factorial. I'm not sure how much you're satisfied with this Wikipedia's proof. At least I am not satisfied, because this is too sketchy, and when I read this proof, I don't really know what's going on here. Instead, I would like to just call this the idea of the proof. And I will give you another proof which I think is more rigorous, but essentially follows the same idea. To make this proof more rigorous, we're going to write an algorithm, and the algorithm will do the counting for this j of np, or nu sub p of n factorial for us. So my proof below will look like an algorithm. However, for those who think this proof is good enough, please feel free to skip to the next section of the video series. To make the proof more rigorous, we'll examine the integers from 1 to n and their divisors, which are powers of p. Now for each L from 1 to n, we consider the prime factorization of L as, so L is equal to p to the power r sub L times other prime factors. Now we will only focus on this p to the r sub L's power, and we will not write down other prime factors explicitly. Then, what is n factorial? N factorial will be the product of those L's, which will be p to the r1 plus r2 plus Rn times other prime factors. But again, we're only going to focus on this part. And we are going to show that this sum of R1 plus R2 all the way to Rn, now we claim that this sum is equal to the summation of n divided by Pm for m bigger to 1. Now to see this claim, we will count the sum R1 plus R2 plus Rn in a different way. And this way will be our algorithm, the so-called algorithm. What we do is that we first subtract 1 from each of R1 through Rn that are at least 1. Namely, if some R sub I is 0, we will leave it alone. Otherwise, it is at least 1, and we will subtract 1 from them. Now let me ask the audience a question. So how many of R1 through Rn are at least 1? And note that this is equivalent to asking that how many of the n consecutive integers 1, 2, 3 through n are multiples of p. Do you see why they are equivalent? They are equivalent because of our definition for R1 through Rn. Remember, by our construction, n factorial is equal to p to the R1 plus the Rn times other prime factors, where each L is defined as R sub L times other prime factors. So you can see it's precisely equal to the number of integers here that are at least 1, namely non-zero. Because if a particular R sub L is 0, then that particular L is not a multiple of P. And vice versa. If R sub L is at least 1, then L is a multiple of P. So these two questions are equivalent. Now, what is the answer to this question? How many integers here are multiples of P? You think about it a little bit, and you should realize immediately. So how many here? They are precisely the floor of n divided P, many integers that are multiples of P. And now we're going to perform a surgery. The surgery here is we will subtract the floor of n divided P, many ones, from R1 plus R2 plus Rn. Namely, whenever sub R sub L is at least 1, then we'll subtract 1 from there. So in total, we'll subtract exactly the floor of n divided by P times 1. And now we suppose the remaining terms after this operation are correspondingly R1 superscript 1, R2 superscript 1, all the way to Rn superscript 1. And you should be able to see immediately what is the relation between Rk superscript 1 and Rk. So it will be either R sub k or I sub k minus 1, depending whether Rk is 0 or not. And this is further equal to 0 if Rk is less than or equal to 1, or Rk minus 1 if Rk is at least 2. Hopefully you should be able to see this clearly. And now we repeat what we have done above. Now we subtract 1 again from each of R1 1, R2 1, all the way to Rn 1 that are at least 1. And now let me ask you the question again. How many of R1 1, R2 1 through Rn 1 are at least 1? Know that this question is equivalent to how many of R1, R2 through Rn are at least 2 based on our relations, namely the relations here. And again, this question is equivalent to asking how many of the integers from 1 to n are multiples of p squared. Do you see why they are equivalent? If you don't see, again, you go back to this definition. That R sub L is at least 2 if and only if p squared is a divisor of L, or L is a multiple of p squared. So how many of them are multiples of p squared? The answer is, like before, n divided by p squared floor. Because from 1 to n, p squared twice p squared all the way to p squared times n divided by p squared floor are precisely those are multiples of p squared. So in total, we will subtract the floor of n divided by p squared many ones from the sum R1 1 plus R2 1 plus the Rn 1. And again, suppose the remaining terms after this operation are R1 2, R2 2, all the way to Rn 2, where you can see Rk2 is either equal to Rk1 or Rk1 minus 1, depending on whether this guy is 0 or not. And this is in turn equal to 0 if Rk is less than or equal to 2, or Rk minus 2 if Rk is bigger than 2. So this is the relation between Rk2 and Rk. And now we subtract 1 once again from each of R1 2, R2 2 through Rn 2 that are at least 1, and get R1 3, R2 3, all the way to Rn 3. With Rk3 equal to 0 or Rk minus 3, depending on whether Rk is less than or equal to 3 or not. And this algorithm will go on and will terminate in finite steps. And in total, we'll subtract how many? N divided by p factorial plus n divided by p squared factorial plus many ones from R1 plus R2 plus Rn. And in the end, we will turn the sum into 0. And hence, because our subtraction algorithm will eventually turn the sum into 0, that means this sum must be precisely equal to the summation of quantities that we have taken from this sum. And it follows that n factorial, which is the product of the powers of p with exponents R1 plus Rn, is the product of j of n comma p's power of p, with this guy equal to the sum precisely, by definition. And this finishes the proof of Legendre's formula. And hope that this proof looks more formal than the Wikipedia's proof.